A diamond is a carbon crystal. Each carbon atom inside is bonded to 4 other carbon atoms. This strong bond gives the diamond its famous hardness as well as its league-leading thermal conductivity. Small impurities or lattice distortions in the crystal give the diamond its colors. Isolated nitrogen atoms make the diamond yellow, pairs of nitrogen atoms make it brown, green, or violet, and distortions in the lattice crystal structure give pink diamonds their wondrous pink. In the wild, diamonds are formed deep within the earth, about 150 to 700 kilometers, over a long period of time. They are then brought to the Earth's surface through volcanic eruptions. For millennia, the only way to get a big, pretty diamond was to randomly pick them out of geological formations, panning the rivers in the hope of finding something lucky. Today, we can make a big, beautiful, perfect diamond in a piece of semiconductor equipment. In this video, we explore CVD processes for diamond production, for gemstones, and more. I covered the history of diamond synthesis in the previous video. I recommend that you check that video out, but here is a drastic summary. In 1797, we discovered that diamonds were just carbon, so scientists tried to heat charcoal into diamond. That failed because we could not get hot enough. Happens to all of us. Then in the early 1910s, we realized that we did not have to replicate all the conditions of the Earth's mantle to make a diamond. Rather, we can use high pressure in combination with high heat to make a diamond. General Electric first pioneered what we now call the high-pressure, high-temperature method, or HPHT, in 1955. This method requires us to subject carbon to 2,200 degrees Celsius of heat and pressures of 1.5 million pounds per square inch. HPHT methods started off quite crude, but have gradually improved in both quality and yield. By the 1990s, we had large, gem-quality HPHT diamonds in various colors, though most come out yellow-orange. The HPHT method remains the most economical way to produce just any diamond, and there is still a lot of research on it being done. Nevertheless, its high defect rate and long cook time meant that it did not much damage the natural gem diamond industry. Chemical vapor deposition, or CVD, takes precursor materials in a gaseous phase and deposits it onto a substrate. The semiconductor industry can use it to deposit single crystal layers of pure silicon onto wafers. Why not for diamonds too? To make CVD diamonds, we start with a gas-phase carbon precursor, usually methane gas. This methane is mixed with hydrogen or oxygen. This stabilizes the diamond's surface and prevents the diamond from converting into unwanted graphite impurities. Then, we use some form of energy to quote-unquote activate the precursor gases, basically decomposing them into atomic parts. This energy can be delivered in a variety of ways: heat, flames, microwaves, or something else. So, the gases decompose, and then somehow the carbon atoms recompose themselves on the surface of a substrate, usually a seed diamond introduced for this very purpose in the form of more diamond. I say somehow because we remain not exactly sure what is going on behind the scenes to cause this and why, in part because we haven't yet developed tools to observe it as it happens. How does it all work? Nanomachines, son. Let's just accept it and move on. Scientists have been demonstrating the growth of diamond crystals with CVD since the 1950s. The prevailing issues are output quality and scale. There is a quality gradient of CVD diamond available. The highest quality are called optical or electronic grade. These are pure enough for us to take advantage of the diamond's special electrical and thermal properties. On the far other end, we have far cheaper industrial use diamond. Today, HPHT-made diamond grit can be made for less than $1 per carat. Dead cheap. Whatever we would use this diamond for, we need to make it at scale. It's easy to use some lab equipment to produce one or even a few diamonds. The issue comes about when we want to scale that up, which brings new technical problems to overcome. In many ways, it is quite similar to semiconductors. It's easy to make a single, perfect integrated circuit. The problem is when we want to make millions of perfect ICs at a good price. The first successful deposition of diamond at a practical rate, meaning more than a micrometer an hour, occurred in the mid-1970s by the Soviet scientist B.V. Derjagin. His success in using a variety of methods raised eyebrows in Japan. The Japanese took these methods and eventually identified two of the major CVD methods used in the lab-grown diamond industry today: hot filament and microwave plasma CVD. Let's discuss the first one. Hot filament CVD injects energy into the precursor gas mix using a very hot tungsten filament, heated to something like 2000 degrees Celsius. There are a variety of setups and arrangements for these filaments, leading to a diversity of designs. Hot filament CVD does work and is a pioneering method, but there were several serious problems. First, while it represented a breakthrough leap in formation speed, it was still initially too slow. The first experiments produced a growth rate of about 1 micrometer per hour, assuming that you wanted a nice gem diamond of 5 millimeters tall, generally about 2 carats. That will take 5,000 hours or 208 days. To speed things up, scientists introduced nitrogen to the process, but as I mentioned earlier, nitrogen atoms make diamonds come out yellow. Not that there's anything wrong with that. Yellow diamonds deserve the same rights as all other diamonds, but a yellow diamond is not as useful for electronics applications, which was what the team at the time was going for. Lastly, and most seriously, there were concerns about the filament. Over time, it might be affected by carbon corrosion and heat, and it might start to warp and bend, affecting the deposition rate. Worse yet, the filament material, tungsten, can contaminate the growing diamonds. So today, the CVD method most often used to create lab-grown diamonds is microwave plasma CVD, or MPCVD, representing about 50% share of the market. One of the big benefits of the MPCVD method is that it avoids the contamination issues of having a filament inside the reactor. To make a diamond, we start with the substrate, little seed diamonds that we will grow the final thing on top of. They look like little plates, but they indeed are also made from diamond. A single chamber can accommodate up to 18 seeds all at once. The seeds all go inside the reactor chamber, which is then filled with the precursor gas mix. We then bombard that mix with high-frequency microwaves. Early prototypes used the same 2.45 GHz waves used for commercial microwave ovens, largely due to the availability of the tubes. I find that amusing. The microwaves ionize the gas's atoms, meaning that they either lose or gain an electron as those electrons energize. When a significant percentage of the gas items become ionized, we get a plasma. During deposition, we completely immerse the substrates in this ball of plasma. If the substrate surface conditions are heated to and maintained at a sufficiently high temperature, then the precursors will settle on it, and then a diamond will grow. After a few days, how long it takes depends on how large a diamond you want, the diamonds come out in this silver and clear platter-like chunk. There are crusts on their edges and sides. That is all diamond dust and grit. You then use a laser to cut the diamond platter into smaller pieces, leaving you with these raw cubes. These cubes are ready to go to a jeweler for cutting and polishing into a finished, brilliant stone. Speed of growth, especially pure defect-free growth, remains an issue, but it is getting faster thanks to improved reactor designs. Furthermore, we can ameliorate this by growing diamonds in batches in parallel. Today, 2-carat diamond rings cost anywhere near $5,000 or so a pop in Costco. Costco mentions that all of their diamonds are quote-unquote natural, which I presume to mean mined. It implies that only mined diamonds are natural, but that should no longer be the case. In 2018, the U.S. Federal Trade Commission amended its definition of diamond for its jewelry guides. Previously, the guides used to include the word natural in the definition. But MPCVD and other lab-grown diamonds have the same optical, electrical, and physical properties as the mined stuff. The FTC has decided that adding the modifier natural in there is no longer useful. The FTC also allowed for the use of the word cultured to describe lab-grown diamonds. The mined diamond industry fought this, recommending that the FTC only reserve that word for pearls. They know what cultured pearls eventually did to the natural pearl industry. 99% of pearls sold today are cultured. I did a video about it. Widely accepted, cheap, perfect cultured diamonds could similarly overwhelm the mined diamond industry and their substantially higher costs. In 2022, the global gemstone industry generated about $30 billion in total value. Admittedly, my sources for this number are not the best, but the number seems pretty reasonable considering that De Beers, the world's leading diamond company, generated $6 billion in revenue in 2022. Anyway, my point is that there is a lot of money to be made here, and every year, CVD diamond makers are improving the speed and scale of growth. At the same time, the public is warming up to these stones. The gap in prices between mined and cultured gem diamonds is growing. People want cheaper diamond jewelry, and cultured diamonds can take them there. Eventually, the price gap will become too compelling for consumers to ignore, and I wonder what will happen to the market then. In a previous video, I mentioned that De Beers sees the writing on the wall. They're transitioning from once controlling a raw diamond cartel to controlling a jewelry brand. In their vision, consumers will buy brands, not stones, and that is where the value will be. Considering the ongoing price pressure issues in the cultured diamond market, why study CVD diamond technology at all? Right now, there are industrial and university teams all over the world still investing significant money into diamond production. Not because they want gemstones, but because there is a larger opportunity in exploiting the diamond's extreme electric, optical, and thermal properties. The first major commercial use case for CVD diamonds was not for rings, but heat spreaders. Cultured single crystal diamond has the highest known thermal conductivity of any room temperature solid, in some cases outperforming traditional materials like copper and silicon carbide by a factor of 3 or more. This makes them very useful for heat sinks and heat spreaders. These are structures for transferring heat away from its source to cooler areas elsewhere. Since heat is the single biggest reason for electronics failure, it's a big deal. AT&T commissioned the first CVD diamond-based heat spreaders for cooling high-powered laser diode arrays, which send signals through undersea optical cables. CVD diamond heat spreaders help shrink the package and extend its operating lifetime. This funded the development of new techniques to polish and cut CVD diamonds, as well as metallization techniques, which involves applying metal layers onto the diamond for mounting into electronic devices. The heat-spreading benefits of CVD diamond have been mooted for advanced packages and semiconductors as well. Considering the massive thermal issues associated with today's 3D stacked chips, I would not be surprised if the semiconductor makers aren't already sniffing around CVD diamond heat spreaders for options. If you don't think it's a big opportunity, then I just want to remind you that Synopsys paid $35 billion for an EDA software modeling thermal interactions in such 3D stacked chips. There is something here. Before we conclude, I want to thank Ropac, a Taiwanese company based in Taichung, for giving me access to their MP-CVD equipment for filming, as well as their openness in answering questions. An incredible experience to see it all in action. If you're interested in their technology and maybe even buying one of their MP-CVD reactor tools for your diamond lab, get in touch with them. For guys like Ropac, CVD diamonds have more potential than just rings and even heat spreaders. CVD diamonds offer tantalizing possibilities in things as varied as power semiconductors, precision optical lenses for lasers, and even detector materials for fusion plasma measurement tools. The key goal is to find an end-user application that can only be made possible with CVD diamond, not one that merely replaces an existing material. That would be the true diamond in the rough that all of these equipment makers are searching for. Alright everyone, that's it for tonight. Thanks for watching. Subscribe to the channel, sign up for the Patreon, and I'll see you guys next time.